Rao Bhim section 7.4 Orthogonality and orthonormal basis. Definition 7.4.1 V is an inner product space, then we call two vectors x and y in V orthogonal if their inner product is equal to 0, and in this case we use the notation x perpendicular to y. Similarly, a subset A of V is called orthogonal if for all x not equal to y both in A, x is orthogonal to y. And I call it an orthonormal set, orthonormal, if along with this condition I also have for all x in A, the norm of x is equal to 1. For example, this set is an orthogonal set because if I take the inner product of these two, I will get 0. It is not an orthonormal set because its length is 1. Here I am assuming the usual inner product, dot product. If, however, I make this equal to 1, then it is also an orthonormal set. Two subsets A and B of V are called orthogonal if whenever you pick any x in A and any y in B, they are orthogonal to each other. Now here is a mistake that sometimes beginners make. Suppose I consider R3 with usual dot product, and I consider the xz plane as my A and the xy plane as my B. Are these two sets orthogonal to each other? Well, just by looking at it, you might say, yes, they are, because this angle is 90 degrees. But that is not same as the definition orthogonality that we are using. In fact, these two things are not orthogonal because I can take this vector, for example, which vector is basically 1, 0, 0, as my x. This is in A, and also I can take the same vector as my y, because this is also in B. Obviously, this is not orthogonal to itself because inner product of this with itself is 1 and not equal to 0. So, we do not say that these two sets are orthogonal to each other. However, if I take A to be this and B to be consisting of the y-axis, then they are indeed orthogonal to each other. Theorem 7.4.3, the theorem which is generalization of Pythagoras theorem, something we have already discussed and proved in an earlier video. It says that if in an inner product space you take any two vectors x and y, then form their sum, and you want to find out the norm square of that, that will be equal to the sum of the two norm squares if x and y are mutually perpendicular. More generally, if I have x1 to xk, and that forms an orthogonal set. That is, if you take any two distinct xi's here, their inner product is 0. In that case, form the sum, take the squared norm, that is same as first taking squared norm and then taking sum. So, once you prove this, this just follows by induction. I am not proving it here because we have already proved it in one of our earlier videos. Theorem 7.4.4, we start with an inner product space V and I take any subset which is an orthogonal subset with the condition that 0 vector is not in A. Then the set A must be linearly independent. Now, first let's understand the intuition. Suppose A consists of only two elements. So, I have this and I have this. So, this is an orthogonal set. I am drawing pictures as if I am in R2. And in that case, I see that these two directions are mutually orthogonal. Now, what is meant by linearly independent? If I take two vectors that are not along the same line, like this or this, then I will have linear independence. So, these are the situations of linear dependence. So, if I have any two vectors that are not along the same line, I will have linear independence. Now, this must be a special case of that because in this case, they are not along the same line. In fact, they make a 90-degree angle. So clearly orthogonality should imply linear independence, and also I must not allow the 0 vector, because if I take the 0 vector, then that vector is orthogonal to everything because it does not have any direction. Inner product of any vector with 0 will give you 0. So 0 vector is orthogonal to everything. That of course does not fit the bill, because the 0 vector may be considered to be perpendicular to this, at the same time it may be considered to be along this vector. That is why I need this condition. However, this intuition works for only 2 or finitely many things. Now, this result is true even if A is an infinite set, which is a possibility that will happen only when V is an infinite dimensional space. Not that we are considering such infinite dimensional spaces here. However, this result is true in general. The proof goes like this. We start with any finite number of vectors in A and some scalars in the field, which is R or C, such that this linear combination is equal to 0. Remember, the definition of linear independence says that whenever this happens, we should be able to show that all the alpha i's are equal to 0. Observe that A may be itself infinite, but at every step I am taking only finitely many vectors. So that is the definition of linear independence. Now, if you are given this, what you will do is you pick, say, V1 and you apply inner product of this with V1, say, from the right. As a result, you get alpha 1, then V1 with V1 plus alpha 2, V2 with V1. Remember, the fact I am using here is that inner product distributes over its first argument. Plus alpha n Vn with V1, and on that side it is 0 with V1. So all that I did was I applied inner product with V1 from the right. Now since this is orthogonal, all these things must be equal to 0. Only this fellow survives, and this also becomes 0. So you get alpha 1 V1 with V1 equal to 0. Now 0 is not in A, so in particular V1 cannot be the 0 vector, so its norm squared cannot be 0 either. So you can cancel it off and you get alpha 1 equal to 0. So whatever you can do with alpha 1, you can do with alpha 2 also, just by taking inner product with V2 this time. In this way you can show that all the alpha i's must be 0, showing that A is linearly independent. One important difference between linear independence and orthogonality is that linear independence is a set-wise property. So when I say a set is linearly independent, you have to take the entire set into consideration to define it. On the other hand, orthogonality is a pairwise property. You have to take only 2 elements at a time and do some check, and you will get the result. Say for example, if I have a set which is like this, say 1, 0, 0, and I give you this set 0, 1, 0 and 1, 1, 0. Then if I take these two, they are linearly independent. If I take these two, this is linearly independent. If I take this and this, they are also linearly independent. However, the entire set is not linearly independent. That's why I said linear independence is not a pairwise property. But if I am working with orthogonality, suppose I take these vectors 0, 0, 1, then this pair is orthogonal, so is this pair, and so is this pair, and I can immediately declare that A is an orthogonal set. This is what makes orthogonality an easier condition to check. You just check only all the pairs and that's it. Theorem 7.4.5. I start with an inner product space and certain subspaces S1 to Sk. I use this less than or equal to sign, meaning they are not just subsets but subspaces, and they are all orthogonal to each other. That is, if you take anything in S1, that will be orthogonal to everything in S2 and so on. Then S1 plus up to Sk is a direct sum. So first quickly remember what is definition of a direct sum and what is the intuition. So here is one example. Suppose I am working with V equal to R3 and I take S1 equal to just the x-axis and S2 equal to the x equal to y line, which means the span of 1, 1, 0. So everything where x is equal to y and the x equal to y and okay, suppose I make this equal to 0. So it is so x equal to y and z equal to 0 line. And S3 I take to be the z axis. In that case, they will form a direct sum in the sense that if I draw the picture, I have the x-axis and I have this line and I have this line. Well, in this case, they are not all orthogonal because I can see these and these, they are not orthogonal. However, they do form a direct sum, meaning if you take any vector along this, you cannot express it as a linear combination of any vectors from the other things. And similarly, if you take any vector along this, you cannot form it as a linear combination of vectors in the other two SIs. Now, it says that if they are all orthogonal, that is, they are all mutually perpendicular, in that case, you cannot have that. Okay, so the proof is pretty straightforward. However, Rao Bhim gives the proof in a very complicated, garbled way. Now, all that you have to do is to use the appropriate definition of direct sum. The way Rao Bhim takes it, it's a very technical condition. So I shall be using just the intuitive condition. We want to show that no vector in any SI can be expressed as a linear combination of vectors from the other SJs. That is what is meant by saying that they are all direct. Each of them is a fresh contribution over the others. Now, if I just use this definition, that cannot be true because every subspace contains a zero vector and zero vector can definitely be expressed as linear combination of any other vector. Just use coefficient 0. So I need to put the condition no non-null vector in any SI can be expressed as linear combinations of the other SIs. We shall prove by contradiction. So let if possible that condition be violated. So you have found some SI vector which lies in capital SI such that it can be expressed as a linear combination of some SJs, and these SJs also lie in their respective capital SJs. J is not equal to I. You can do this. So I will arrive at a contradiction. And I assume that this is non-zero. So I am going to contradict the fact that they are all orthogonal to each other. So I have got, and alphas are just some scalars. So all these things are supposed to be orthogonal because they are orthogonal to each other. So this S1 to SK, they are supposed to be all orthogonal. So S1 to SK, these vectors are all orthogonal because they belong to these SIs. So I know that they must be linearly independent. But how is that possible? Because if I take everything on that side, I am going to get this. This is equal to 0. Now, if this is equal to 0, then obviously I am having coefficient, here at least I am having a coefficient equal to 1. So I see some linear combinations of these becomes equal to 0, where at least one coefficient is non-zero. And that immediately shows that this result cannot be true. So they are linearly dependent, but they are orthogonal, so they must be linearly independent. And that gives you a contradiction, completes the proof.